Thank you. So, yeah, something a bit different now. So I work at the Animal Health Laboratory, which is part of the Ministry for Primary Industries in New Zealand. And I'm really here representing Dr. Joseph O'Keefe, who is the director of the project to build our new biocontainment laboratory. So the first question, I guess, is why are we building a new laboratory? And really, I guess the first point to make is that the high containment laboratory we have is New Zealand's only high containment laboratory. We don't have any regional laboratories or a network of other labs that can do this level of work. The lab we have was commissioned in 1998, and it had a design life of about 15 to 20 years, so it's rapidly approaching the end of its design life. As a consequence of this, it's requiring increasing maintenance and is increasing downtime. In addition, it's poorly designed for some of the work that we now do. So when it was designed, for example, we didn't routinely do molecular diagnostic testing. And it also, in terms of the way it was built and designed, it lacks flexibility. Oh, something's a bit strange happened there. But I guess the main aims of this new laboratory are to improve the ability for New Zealand to identify and manage high-risk animal diseases, to help maintain, our reputation in the international community, to provide services that meet both business as usual and surge requirements, obviously to provide a safe and secure working environment, and very importantly, from an operational perspective, to make the services efficient and maintainable. So the project started back in 2012, where we had an extensive period of gathering user requirements between the design company Merrick, who are based in Canada, and ourselves. And then we've gone through, obviously, the interesting process of acquiring funding and approval from the government. And now we're kind of in the middle of the construction phase here, and we're hoping to be in the laboratory in early 2019. I just wanted to highlight a few of the important strategic factors that we had to consider when we were designing this laboratory. So as I've mentioned already, it is the only laboratory like this in New Zealand. So things like capacity, operational capability, the resilience of the building, the ability for it to keep operating, the fact that it's going to have shared use. There are going to be health-related work going on in that laboratory as well. And in New Zealand, we don't have an established biocontainment industry. So when we looked at this in a bit more detail, we developed some detailed requirements. Sorry, it's a bit smaller writing up here. But essentially, when we've looked at capacity, obviously we have to be able to cope with all the emergency exotic animal disease samples that we get in New Zealand. We can't send them anywhere else because there is no other lab. Therefore, we have to be able to use the maximum use of the space available, and we need to be able to meet the different requirements of our stakeholders, whether that's the government, industry, or the New Zealand public. In terms of our operational capability, there's going to be a range of different science disciplines working in that laboratory space. We looked quite closely at whether we needed to have a PC4 laboratory in New Zealand. For a range of reasons, we decided this wasn't appropriate, but we did acknowledge that we needed to have the ability to potentially inactivate samples that may contain risk group 4 organisms before we send them elsewhere. And the other thing that we had to bear in mind is that all the work we do isn't all at high containment. We do a lot of our work at PC2 level as well. In terms of resilience, of course, with these laboratories, it's very important to have redundancy in your systems and as few single points of failure as possible. And it was very important, again, in the New Zealand context, to have a very collaborative approach with the regulators. With the shared use, we're going to have separate lab space inside high containment that's used by another organization. But we will work closely with that organization, especially in emergency disease situations. So, of course, there's a need there to have shared operating procedures. And in relation to the lack of biocontainment industry, we wanted to keep things in terms of the construction as simple as possible, and likewise with the maintenance of the laboratory. And wherever possible, we wanted to be able to bring in components from overseas. So the big question whenever you're building a new laboratory like this is how big should it be? Because you can make it as big as you want, but we wanted to make quite an informed decision based on our situation. So we used foot-and-mouth disease as a model of maximum demand. And we reviewed experience of the UK 2001 and 2007 outbreaks. And we commissioned Professor John Wildsmith and Professor Roger Morris to model the lab usage during those responses, and then we could apply that to potential outbreak situations in New Zealand. And using that approach, we were able to develop an estimate of the number of samples we could expect with our testing algorithms based on a number of infected properties that we might see. So this is just a representation of this. You've got the number of infected properties, which goes up to about 100, versus the number of samples. So this is an estimate, and in reality it could vary, but it gives us a pretty good idea. And the reason we went up to the 100 infected properties is based on historical data. The majority of outbreaks that have occurred have been between 1 and 100 infected properties. And bearing in mind New Zealand's extensive biosecurity systems, we would hope that if we ever did get an incursion, we would pick it up quickly and we could minimize the size of the outbreak. So that really was the decision we made. We made the decision that we needed a laboratory that could handle samples for an outbreak of up to 100 infected properties. And that equates to about 51,000 samples. And with our testing procedures, that would be approximately 100,000 tests per week. So I'm just going to move on to some of the key design responses that we came up with. Firstly, the design aspects we had to consider, and then some of the responses as well. So in New Zealand, we have a requirement to have a high level of seismic protection, and I'll talk about this in a bit more detail. Obviously, we wanted to have both enhanced physical containment 3 laboratory space, but we also needed PC2 as well. We wanted to have enhanced air filtration for the 2 laboratory floors that we were going to have. The reason being that we wanted to be able to operate the lower floor that would normally operate at PC2 level as an EuFMD contingency laboratory, so ramp it up to PC3. We wanted to have flexible, reconfigurable rooms to meet the different demands we'll have at different times. And I've mentioned already the redundancy, so especially important when we're thinking about our effluent decontamination systems and our air handling systems. And also having these systems scaled to deal with high or surge capacity. So this is what we're building. The laboratory space is going to be about 3,400 square meters over 2 levels. A couple of just quick points to make about the design. You'll notice there's an extensive use of wood paneling on the exterior, so we were trying to be sympathetic to the local environment. We're in quite a rural location, so we want to try and reflect some of the natural materials in the area. And you can just maybe see some of the cross-bracing, so that kind of hints at some of the seismic protection that we've put in the building. So I've mentioned already, Merrick are the company that have designed the laboratory, and the main construction firm is a company called Fletcher's, who are based in New Zealand. And this is just a section of what we're building. On the first floor, this is going to be an enhanced PC3 laboratory space. On the ground floor, that's going to be our PC2 in normal circumstances, but as I've mentioned, can go up to PC3 plus if required in an emergency response. We're going to have 2 floors of mechanical and plant above the laboratories. And then underneath, we've got an undercroft with the base isolation units, and I'll talk about these in a little bit more detail. So time's very limited, so I just want to touch on one of the key design aspects that we had to consider when we were designing and now building this laboratory. So where we're based, the Animal Health Lab, is in a valley just a bit northeast of Wellington, which is down here. And you can see there's a nice big fault line that runs really close to our laboratory, and this is one of the major fault lines in New Zealand. So we are at major risk of a serious earthquake in the next 50 years. But, do please come and visit if you're ever in the area. So, of course, we want to build a lab that is going to be protected as much as possible in the event of an earthquake. So some of the requirements around that is we wanted to build a lab that meets this importance level 4 requirements. So importance level 4, it means it's a building that is required to be operational after a natural disaster such as an earthquake. We want, this is a very, very important point, we want to be able to maintain containment if at all possible. We want to be able to protect our staff by bracing all laboratory equipment. The last thing you want is there to be an earthquake and a huge incubator landing on you. We want, after an earthquake, to be able to fully inspect the building and the facilities to see if it's safe to go back in and to get it operating again. And also, if it's not a particularly major earthquake or we know it's safe to continue working, we need to have the utilities to keep the laboratory operating. So this led us to some more detailed requirements. So in terms of the structural side of things and protecting the building, having it base isolated, which helps avoid cracking of walls and breaches of containment, having a bracing system that allows laboratory staff still to easily move equipment. It's not stuck in one position and that's it. Being able to get into the spaces and inspect areas after, in the event of an earthquake, and also to have backup systems, especially for water and electricity. So these are the responses that we produced. So firstly, the laboratory needed to have a really rigid structure and to be base isolated, and I will get to what base isolation means. To have flexible wall to slab connections to minimize the chance of cracking and breaches of containment. Have a universal bracing system in the laboratory. Having services that are fully inspectable, and then having backup generators and water tanks actually within the building itself.
1 minute, Richard.
Sorry, okay. So, very briefly, the laboratory is a very rigid steel structure, and it sits on base isolation units with essentially lead rubber bearings which allow the building to move in any direction. So the building will move, but the actual walls will stay static. We also have these big hold-down piles, so these essentially anchor the building into the ground. Back in 2011, there was significant earthquakes in Christchurch, where the vertical acceleration that was generated lifted buildings off the ground and destroyed them. So obviously, this is a way of trying to mitigate that risk. And then we want to have flexible service connections, so if the building moves, it doesn't rupture all the services. And this is just a representation of this as the lab's being built, the hold-down piles. I'll just point out the rattle space. So right around the lab, there's about 1 meter space all the way around. So this is the space that the lab can move into when it's shaking. And that's just showing that now. So we're now at the stage where we've got the ground floor. This is the undercroft under here with the base isolation units. And this rattle space will have concrete slabs over the top. But if there's an actual earthquake, those concrete slabs will just shatter so the lab can move. And this is where we're up to now. So we had some old labs in here that we've now demolished. I should say our existing high containment lab, which is here, is still operational and will continue to be operational until the new one's up and running. And yeah, I guess I'm out of time, so I'll leave it there.
Thank you, Richard.
Thank you.
That was fascinating. Any questions? Yeah, Janko, you have a question.
This one. Okay, thank you. This is new laboratory, and we're talking about biosafety. But what about biosecurity? Because nowadays, with this bioterrorism, there was one symposium where the Americans proposed to distinguish between biosafety as measures against non-intentional mistakes that could happen, and biosecurity as measures against intentional interventions from person that should not be in the laboratory, should not have something common. I mean, now you have the chance to do that, what you envisaged.
Yeah, so that was a very important. I didn't talk about it in this presentation because of time, but yes, the security aspects are a very important consideration. So we've done a lot of work in this area, and we're going to have a lot of systems in place to manage that. So, for example, we're going to have cameras in all our laboratory and storage areas within the containment area, and the whole entry and exit process will be a lot more robust probably than it is now.
Michael has a question. Oh, maybe Michael first and then this gentleman.
I want to ask the obvious, if kind of impolite question, how much?
So the budget for the project, the budget for the project is 87 million New Zealand dollars.
The maintenance cost or
The operational cost per year. I believe I couldn't give you a definitive answer, but I think it's around about 2 million New Zealand dollars a year. That's the anticipated cost, although of course whether it works out like that, I'm not sure.
Thank you very much, Richard. That was a really interesting insight into the process. I mean, there's so much to go into this thing. You really explained it very clearly. So thanks again to Richard. Some other questions. And now we're joined